So today we're going to look at another application of the integral. We're going to start looking at volumes. And we're going to be looking at volumes two different ways. So we'll have one way we'll look at today, and then tomorrow we'll look at another way. But here's the idea behind volume by slicing. We've got a nice little visual here for us. Let's say you've got a region in the plane that's going to act as your base. So what we got here, welcome in. This is your base. So we're thinking of this thing as being your base. So that's your base right there. And then what we're going to do is we're going to make a solid from this base using known cross sections. So for example, let's say I wanted to build this by looking at square cross sections. So what I would do is I'd be taking this base and I'd be chopping up the base parallel to the y-axis, and all these little representative rectangles that we had were going to be realized three-dimensionally as squares. So as you move through this solid, you'd have squares, and the squares would have different sizes because the dimensions of the square are determined by the height of that representative rectangle. Are you with me or not? Okay. So we can visualize a solid as being grown, and we visualize that solid as being infinitely many of these little cross sections. So can you visualize the process of what's going on here? Okay. Now another way is we could start with the solid and slice it up into pieces. And so you take like a loaf of bread, you slice a loaf of bread up into very thin pieces. You can measure essentially the area of each of those slices times the little width of those slices. Add all that up to get your area. But that's kind of what's going on here in this formula. If A of t represents the area of cross sections of a solid obtained by slicing the solid perpendicular to the t-axis, the volume of the solid given is this. So essentially we're looking at the volume here. If I look at this sort of at the level of units, as the integral from a to b, a of t dt. So volume, we're looking at cross-sectional area times thickness. And so if you take area times thickness, that gives you a volume, and then we're adding up the volume of all these slices. So basically volume is equal to the sum of the volumes of the slices. So does that principle make sense? So just like area was something you could chop up and add, volume is something that you can chop up and add. So first example here, we've got this nice visual to help us. Let R be the region bounded by the graphs of y equals x squared and y equals root x. Find the volume of the solid whose cross sections perpendicular to the base and parallel to the y-axis are the following three shapes. So the first thing you always want to do in this scenario is you want to sketch the region, which hopefully after doing the area between curved sections, you're good at that. And once again, you've got Desmos to help you as well. But we've got y equals x squared, y equals square root x. You can find their intersection points. And so, once again, this is going to be the base of the solid. And they tell us that the cross sections are perpendicular to the base. That means that this is literally the bottom, and parallel to the y-axis. So that means when I think about my representative rectangle here, it's parallel to the y-axis. So this is how I'm slicing this thing. Right? So if your cross sections are parallel to the y-axis, that means you're chopping up the what axis? You're chopping up the x-axis. Make sense or not? Okay. So my volume for all of these problems is going to be an integral. We're chopping up the x's from 0 to 1. Whatever the cross-sectional area is as a function of x times the dx, think of that as your thickness. So once again, it's cross-sectional area times thickness. You're adding all that up to get the volume. All right, so in number 1, we're looking at squares. So once again, let's go back to this nice visual we have. So there's our base. Once again, we are looking at cross sections perpendicular to the base, so they'd be standing straight up from the base, parallel to the y-axis. So this is what we're doing. As we chop up the x's, we're going to be moving our representative rectangle through that region. And what shape are we putting on top of that, right? So that's the location. What top? We're putting a square on top of it. And so what my integral is going to do is my integral is going to start at 0, and it's going to sweep through to 1, and it's going to be calculating the area of those squares as x runs from 0 to 1, and it's going to be adding those up. Integrating means bringing together, adding up the area of that square times the infinitesimal width to give us the volume of those slices. And so what the integral does is it's building up as you go from 0 to 1. It's building up this solid. Whoops. And so then that would be the resulting solid. Okay? So there's a link to this in the Blackboard, and I encourage you to play around with it. It's a very nice visualization. Okay? You get the idea? Now I got to figure out what that area, that cross-sectional area formula is. So to get the area of a square, well, how do you get the area of the square? You just take the length of one side and do what? Square it. You follow? So now we go back to our little picture here. Once again, we got a representative rectangle. And what's going to be the length of the side? Well, the length of the side is going to be the height here. You follow? So my a of x in this case is just going to be this, right, but squared. And how do I figure out how tall this rectangle is? Think back to what we did yesterday. I'm going to take the top minus the bottom. What's the top curve here? Square root x. What's the bottom curve here? X squared. So that a of x represents the area of that square at position x. Okay? So for example, to kind of show you what's happening here, let's fire up Desmos here. So a of x is root x minus x squared all squared. And this is looking from x between 0 and 1. There it is. So for example, a at 0 is 0 because when you're at 0, right, there's no height. You can see where it maxes out. Maxes out right around there. That's going to be the biggest square at roughly 0.3969. So if I look at this and see if that tracks, let's take a look here. Back to 1. So as we go through there, x equals 0. There's no square because it's 0. But as I move from 0 to 1, the biggest square should be around what? 0.39, 0.4. So you see how the squares are getting bigger, and then they start to do what? Get smaller, right? So do you see what the a of x is calculating? A of x is calculating the individual area of each individual slice. So I'm going to take that slice times the dx, that's your width, get a volume, then add it all up. So my volume then would be the integral from 0 to 1 of my area dx. Okay? And once again, we're not going to go through this. This is the Calc 1 integral. What would be the first thing you would do to evaluate this integral? Yeah, you have to FOIL this out, right? So you go ahead and FOIL that out. Then you're left with a bunch of power rules and sum and difference rules. You follow? And if you go through that, and I encourage you to do so if you need the review, I got the answer there. So 9/70 units cubed. And so these are volumes, so everything's going to be what? Cubic units. Okay? So now, let's shift the shape. So everything's going to be the same. I'm still looking at the same base. I'm still going to look at these as creating cross sections perpendicular to the base. So once again, they're coming straight out at us from this perspective. They're coming straight up. But now instead of squares, I'm going to change the shape and make them equilateral triangles. Okay? So I'm going to be growing equilateral triangles. I'm going to be putting them in here. And as I move through, there we go. So I'm going to be growing this solid as that. Okay. Now, can you think of a modern day place you would actually see this sort of solid, how the solid would get generated this way? You can go across the street to the makerspace. You ever heard of 3D printing? Isn't this kind of what 3D printing does? It puts down one layer at a time. You follow? Now, if you want to get outside, although be careful because it's supposed to get really hot, you can go over to Hogback Ridge or some of these metro parks. You go in and you look at the little waterfalls, and the waterfalls have these very thin layers of, I think it's slate. Is it? No, is it slate or shale? Shale. But you have basically these waterfalls, the contours are made by these infinitely thin, or very, very thin little layers. That's exactly what's happening. We're building this all from layers. So it's like 3D printing. Okay? Okay, so what do we need to do here to figure out this volume? Well, once again, the volume is equal to the integral from A to B. We are chopping up the x-axis. Once again, how do we know we're chopping up the x-axis? Because it tells us that I've just got too many tabs open here. It tells us that the cross sections are perpendicular to the base and parallel to the y-axis. So the cross sections are parallel to the y-axis. That means we're chopping up the x's. So that means that we have to get everything in terms of x's. And so my area now are equilateral triangles. So I have to think back to, geometry here. So here's the base of that equilateral triangle. And to get the area of the triangle, I need 1/2 the base times the what? Height. Okay, so how do I get the height in there? So if it's equilateral, then what are all these angles? They're all what? 60 degrees. So I could get the h over the base would be the tangent of 60 degrees. So h would be the base times the tangent of 60 degrees. And what's the tangent of 60 degrees? Yeah, √3. So h is equal to √3 times the base. So I put that back into here. I get the area is going to be 1/2, well, times √3, so √3 over 2. Times the base what? squared. You follow? Everybody okay on the geometry there? Now, luckily for us, I already know what the base is. You follow? Because once again, what does it tell me? I'm looking at cross sections that are parallel to the y-axis. Parallel to the y-axis means I'm chopping up the x's. So my base is going to be this length, which is exactly what it was before. So it's the top minus the bottom. And I'm ready to go. Any questions on the setup here, folks? Do you see what's happening? Do you understand the big picture process here? All right, so my volume is going to be the integral. I'm chopping the x up from 0 to 1. I need to find the area of that equilateral triangle. The area of the equilateral triangle is root 3 over 2 times the length of the base squared. The base is going to be the top curve minus the bottom curve squared dx. And this is just going to be root 3 over 2 times the volume we had before. You follow? Because it's the same integral. Oops, wait a minute. I got a 4 in there. What did I mess up? I think I got the area wrong. Oh, I'm sorry. Yeah, I did get this wrong. Hold on. This right triangle here, this is not the base, but this is the base over what? 2, right? So it's a base over 2 there. So I apologize. There we go. So this would be root 3 over 4. So this would be root 3 over 4. Is that a question, or is that someone dropping out or popping in? Why is the base squared? Because we're looking at the area. We're looking at the area here of this triangle. So this is the formula for the area of an equilateral triangle. It's root 3 over 4. It's 1/2 base times height. But if it's an equilateral triangle, I can get the height as root 3 over 2. So that's getting plugged in for the height. Okay, so that's your area. And then this would be whatever cubic units. So you draw the base. You decide what axis you're chopping up. If they tell you the cross sections are parallel to the y-axis, that means you're chopping up the x's and draw your rectangle in there. If you're parallel to the x-axis, you're chopping up the y-axis, draw your rectangle in there. You draw that same representative rectangle, and then from that you figure out what the area formula will be. All right, now semicircles. So once again, we've got the same setup. So this is going to be the base. They tell us that the cross sections are going to be perpendicular to the base, so they're going to be standing straight up from the base, parallel to the y-axis. That means you're chopping up the x's. But now we want them to be semicircles. So when we look straight down at the object, there's our representative rectangle moving through there. But on top of the rectangle this time, instead of having squares or instead of having triangles, we're going to have what? Semicircles. So what does that look like? Well, it's going to look like that. And so you have to imagine this solid being built up of these semicircles. So anytime you slice it, you're going to get a semicircle. And so here's what that solid will look like. Okay. So once again, I have to go back to geometry and figure out what's the area of a semicircle, and then how can I get that in terms of x. So let's take a look at my base here. So y equal root x on top, y equal x squared on the bottom. I'm going to draw my representative rectangle there. And that's going to be the base of a semicircle. So if I think about what's happening is I've got my representative rectangle here, and I'm going to grow a semicircle on top of it. So this is one of my cross sections. You follow? Now, how do I get the area of a semicircle? It's usually phrased in terms of the what? Radius, right? So the area of an entire circle is pi times the radius squared. A semicircle is pi times the radius squared over what? 2. So I need the radius here. You with me or not, folks? So how do I get the radius? Well, the radius is going to be half the diameter. So the diameter of this semicircle is going to be the top minus the bottom. That's root x minus x squared. So the radius is going to be half of that. Does everyone see how we're getting the radius for that? Now I just pop that into the formula. So the area here is going to be pi over 2 times the radius squared, which I can simplify to pi over 8 times the integral I had at the beginning. So now to get the volume, what do? I take the area of this semicircle times the little width dx, and that'll give me the volume of that slice, and then I add all the slices up as x runs from 0 to 1. Once again, this would be pi over 8 from what we got from number 1, units cubed. Okay. You see the process, folks? You sketch the base. If the cross sections are parallel to the y-axis, you chop up the x-axis. Draw your representative rectangle. How does what you drew figure into the shape that they want? Alright, so once again, this is here for you to play with. I encourage you to play around with it. Let's take a look at number 2. Find the volume of the solid with a circular base of radius 5, whose cross sections perpendicular to the base and parallel to the x-axis are equilateral triangles. Alright. So now, circular base of radius 5, cross sections perpendicular to the base, parallel to the x-axis are equilateral triangles. So the idea is, and now we're going to try to visualize this, is we're going to have this circular base, and we're going to have the cross sections parallel to the x-axis. And we're going to, from these cross sections, we're going to grow equilateral triangles. You follow? So that's kind of the setup here. So let's try to model this now in the plane. So I need a circle of radius 5. Now it doesn't tell us where the circle is centered. Does it matter where the circle is centered for this? We're finding a what? Finding a volume. Does it matter the volume where the thing is situated? Like if I have this object here, or I take it over to Adam's desk, the volume is going to be what? The same. So what's the easiest place to center the circle? origin. So that's what we'll do. So that's the equation of the circle centered at the origin, radius 5. We'll put that in there. So this is our base. Okay? So this is what we're going to be growing these things on. And it says they want that, what? They want the cross sections to be parallel to the x-axis. So if the cross sections are parallel to the x-axis, that means we're chopping up the what axis? So here's the cross sections, right? Parallel to the x-axis means we're chopping up the y-axis. Okay? And that means that the infinitesimal width here is going to be, that's going to be your delta y, that's going to turn into your dy. So the volume formula is going to be the integral from a to b, a of y dy. So we need everything now expressed in terms of y. You follow? And in fact, let's go ahead and plug this in. I'm integrating between what two y values? Negative 5 to 5. And so I got to figure out what's a of y. So once again, what am I growing from these from the base? I'm growing up what? Equilateral triangles. Okay? So I know that the area is the area of an equilateral triangle. I know that that's root 3 over 4 times the base squared. We all cool with that? Right? That's the formula we derived just a little bit ago. So going back to our picture here, right? This is what we're growing. So this is the base. We need the base now in terms of y. So I go back to my picture. This is x squared plus y squared equals 5, or 25. I've got to figure out how long that is, right? So I think back to what I did yesterday. If we're chopping up the y-axis, you turn your head sideways. Instead of taking the top minus the bottom, we take the what minus the what? Take the right minus the left. So what's that in this case? Well, I got to take this equation and solve it. X as a function of y. And what happens when you do that? You subtract over the y squared, and then you'd have to take the square root. You follow? So you're going to get a plus or minus square root. Which of those is the right half, and which of those is the left half? Is the right half the positive x's or the negative x's? Positive x's. So that is the positive 25 minus y squared. And this is the what? Negative. So we take the right minus the left. What's going to happen though, folks? You can see it geometrically. These two things are going to subtract. I'm subtracting a negative, which really means they're going to just double up. Yep. There it is. So at any given y value, this represents the length of that base of what's going to be turned into a triangle. You follow? Let's test this out. What should it be down here? This is when y equals what? What's the y value here on the x-axis? It's 0. If I plug 0 into this, I get the square root of 25, which is 5, times 2, which is 10. Does that make sense that this is 10 units across? Yeah, because we're right at the diameter of the circle. And you can look at the extreme values. If I look up here, plus or minus 5, right, there's You get 0 out. So that means my area as a function of y is root 3 over 4 times the base squared. And this is actually kind of nice because look what happens. The 2 squares to give you a 4, which cancels out the 4, and I got root 3 then. And what happens to the square root? That cancels out as well. So you get an integral that really isn't that bad. So my volume would be the integral from minus 5 to 5, square root of 3 times 25 minus y squared dy. Now, you can do a little better than this too, right? We talked a lot on Monday about exploiting symmetry when we were doing those polar graphs. There's symmetry abounds here. You follow? The base is symmetric about the x-axis. The solid itself will be symmetric because that's how we're growing the solid. So instead of integrating from negative 5 to 5, I could just integrate from where to where? I could integrate from 0 to 5 and just do what with my answer? Double it. Make sense? And then there you go. Once again, all your answers here in this section are going to be units cubed because we're finding volumes. Any questions on this example? You get the gist of this. Here's the base. We're going to lay it flat, and then we're going to grow cross sections from the base with various and sundry geometric shapes. So you need to figure out what the area of those shapes are in terms of the variable you're integrating. And you're really just basically thinking of this solid as being an aggregate of all these cross-sectional areas. All right, so that's a very powerful idea. Just like we thought of the area under a curve as being the aggregate of all those infinitely small rectangles. All right, we got a special case here of this called solids of revolution. So let me get the, I thought I had this open. I'm getting lost in the tabs. I guess I don't have it open. Let's try this. Okay, so a special case of volume by slicing is when you create what's called a volume of revolution or a solid of revolution. So here's the idea. You're going to take some region in the xy plane and you're going to spin it around one of the principal axes. So in this case, we've got this region. I'm going to spin it around the x-axis, and it's going to rotate out this shape. Okay. So we're going to get this. We're going to get this shape at the end. See what's happening there or not? Now notice, because I'm spinning it around the axis, I'm going to make a bunch of cross sections, all of which are what? Circles. You with me or not? Okay. And the radius of those circles is just going to be whatever that function value is. You follow? So if I think about this, once again, going back to the start of this, with my tried and true representative rectangle, the representative rectangle sweeps around and creates what they call a disk. So that's what they call that shape. You follow? Really what it is it's a very squat cylinder. You follow? So if I think about what the volume of this is, I call that the radius. I'll call that the thickness. The volume of a disk is going to be the area of the base, which is pi times the radius squared, because it's a circle, times your thickness. Now, depending on what axis we're spinning it around, the thickness is either going to be your delta x or your delta y. And then, depending on what axis you're spinning it around, your radius is either going to be your f of x or your f of y. So once again, we're thinking of this solid of revolution as being an aggregate of these disks all stacked together. So, key idea. There's your governing formula for that. So, let's do an example. Find the volume of the solid obtained by revolving the given region about the stated axis. We're going to look at the region bounded by this. This was the one in the picture about the x-axis. Okay, so here we go. First off, you want to draw the region. Once again, feel free to use Desmos. If it's a complicated region, fire up Desmos and draw it. Okay? So here's the region they're talking about. So that's step one, is figure out the region. Step two, now we want to figure out what we're rotating around. It tells us we're rotating around the what axis? The x-axis. This is the axis that you chop up. So I'm going to be chopping up the x-axis. Now it's time to do what? Draw your representative rectangle. And remember that the volume of the disk is pi times the radius squared times your thickness. The radius is always going to be your function value. So think of it this way, the radius is always going to be, in this case, right, here's your radius. It's top minus bottom. And then your thickness is always going to be the delta x or the dx, or delta x or delta y, depending on what you're chopping up. So in this case, this is going to be your delta x or delta y. In this case, it's going to be delta x. So the volume of the disk is going to be, integrating, we're going from 0 to 1, pi times the radius of this disk. Well, that distance there, it's going to be x squared. Squared, so that's the radius squared times your thickness, dx. Yeah? Oh wait, we're supposed to go to 2? Oh yeah, sorry, thank you. Yeah, we're going to 2. So once again, you want to think about each of these. So this is your pi. This is your radius. Squared. And this is your thickness. So when you spin that graph around, that's your radius, and that's your thickness. Okay? And then you're on your way. So this one isn't so bad. What happens if you have a power to a power? What do you do with the powers? You multiply them. Okay? And that one ain't so bad. Okay? So you want to think, if you're doing the disk method, you're doing a solid revolution, you're chopping up the axis of rotation. Draw the region, draw the representative rectangle, what's your radius, then you're on your way. Let's look at number 2. Very similar. What's the change? Instead of being bounded by y equals x squared and y equals 0, revolved around the x-axis, now I've got y equals x squared, y equals negative 1, and now we're rotating about what? The line y equals negative 1. All right. So it's essentially the same picture. So we're going to 2 now. Can't forget that. We're down here. Y equals negative 1. So the region now is bounded this way. So that's our region R. We're spinning it around the line y equals negative 1. And so once again, you're drawing your little representative rectangle. You spin that around, you're going to get yourself a little representative disk. Remember, the radius is always in the middle, and the thickness. So, using the disk method, we always chop up the axis we're spinning it around. So we're chopping up y equals negative 1, and each of those pieces means we're chopping up what variable here? We're chopping up the x's again. So my thickness is still delta x's, but what's my radius? So my radius is going to be how tall this representative rectangle is. So once again, we think back to yesterday. You're chopping up the x-axis. We'll take your top minus your bottom. So the radius here, once again, that's top minus bottom. The top curve is y equals x squared. The bottom curve is y equals what? You with me or not, folks? So that distance from the curve to the axis of rotation is x squared, gets you to the x-axis, then I have to go an additional what? 1 unit. Does that make sense or not, folks? So now to get my volume, it's pi times the integral from 0 to 2, radius squared, x squared plus 1 squared, times your thickness. And as with that first integral we talked about, what would be your first step to evaluate this integral? FOIL it out. And you get that. Okay? So next example, let's look at this unbounded region. So we're looking at y equals 1 over x for x bigger than or equal to 1. And so this is an unbounded region, spinning this thing around the x-axis. All right? This shape actually has a name. This is called Gabriel's horn. It's also called, I think it's called Torricelli's trumpet. Gabriel's horn goes back into the Christian tradition of angels. So there's this angel named Gabriel, and when he blew his horn, interesting things happened. It's called Gabriel's horn ostensibly because this is one of these objects that just goes on forever. Right? There's no end to it. You follow? Which is ostensibly why you need a supernatural being to wield it. Anyway, let's figure out what the volume is. So once again, you're chopping up the axis of rotation here, which is the x-axis. There's your representative rectangle. So you've got your disk. You got your width here. That's your delta x. You need your radius here, which is going to be your f of x. Oops. So it's your radius in there. Top minus bottom, in this case, is going to be 1 over x. And so what's your volume? It's going to be pi integral. Now we're starting at 1, but we're never ending, right? But we know what that means, right? We talked about these a couple weeks ago. The integral would just go off to what? Infinity. 1 over x squared dx. And this would calculate the volume of Gabriel's horn. Now we know from improper integrals that this integral will in fact what? It'll converge because in fact we know the answer to this one. I think this works out to be 1. So you just end up getting pi units cubed. So even though you have this trumpet that has an infinite extent to it, you could fill it up with pi cubic units of paint. You follow? That's what it means. Okay, that's how we're interpreting this integral anyway. All right, let's take a look at a more complicated region here. Let's look at the volume obtained by revolving the region bounded by y equals x squared and y equals root 8x about the x-axis. So look at y equals x squared, y equals root 8x. Once again, the first thing to do is graph the region. So we've got the y equals x squared, we've got the y equals root 8x. And once again, you've always got Desmos here to help you out. We need to know the intersection points. So once again, you can set these equal to each other. You're going to get, what, 0 and 2? We're rotating it around the x-axis, which means we're chopping up the x-axis. We draw the representative rectangle. But what's different about this representative rectangle as opposed to the other ones we've done? The rectangle does not extend down to the axis of rotation. You follow? So you don't get a disk when you move this around. What do you get? You get a disk with a hole in it, right? This gap here is going to generate a hole. So here's this scenario. Got the representative rectangle there. So look what happens as I move this around. Or maybe it won't move. Here we go. Here we go. So when you move this around, you see what's happening with that gap? It's leaving a hole in the middle. You follow? So this, in the business, this is called a washer. But I like to just think of it as a disk with a hole in it. And once again, how do you identify your disk is going to have a hole in it? If you have a gap between the bottom curve and the axis of rotation. Make sense or not? So here's how I like to do this. They call this the washer method, but I just, so they have the washer method. Yeah, I could spell. So here's the idea, is we're going to take the whole volume minus the whole volume. So whole minus whole. See, it's a play on words. So what do I mean by that? Here's what we're going to do. This is the volume that we want. You follow? That's going to be this volume, this entire volume, the whole volume, minus the whole volume. Does that make sense or not? Okay. So you can think of, from the axis to the top curve, sometimes I call that the outer radius, because it's the outer radius, which means that the distance here would be the what? Inner radius. So the washer method looks like volume is going to be pi times the outer radius squared times your thickness minus pi times the inner radius squared times your thickness. But do you see the subtraction of volumes there, right? So I take the whole volume minus the volume of the whole volume minus the whole volume. So that's what's going on there. Okay, so let's complete this problem then. So we got that. We got that. This is y equals root 8x. This is y equals x squared. We draw in our representative rectangle. We realize, wait a minute, there's a gap between the bottom and the axis of rotation. So we're going to do some subtraction. So we'll take the volume of the whole thing, so from the top curve down to the axis of rotation, and then we'll subtract off the volume that way. You follow? So my volume is going to be, I'll try to keep the color coding here, pi times the integral from 0 to 2 root 8x squared dx minus pi times the integral from 0 to 2 of x squared dx. So this would be what we were calling the whole volume minus the whole volume. Make sense or not? You see what's happening there geometrically? And once again, the key to this is what you do. It goes back to what we did yesterday. It's just really what we go back on Monday. You draw the region, you sketch in the representative rectangle, and then from that you put it all together. Now what you'll often see is you'll just see, since it's the same, both of these integrals have a factor of pi. Both of these integrals are going from 0 to 2, so they'll often write this more compactly as a single integral. Oop, I forgot the squared on this one. So you'll often see it written that way. But you're squaring, but I think it's best to think about it this way, because there's a common mistake I'm not even going to mention because I don't want to put it in your mind at all. But if you just think of you taking the whole thing minus the whole thing and writing it up that way, you'll avoid that common mistake. All right, well, let's look at this same region, but now let's spin it around the line y equals 5. Now, let's see, we got the y equals root 8x. Yeah. We got the y equals x squared. Now when I plug 2 into the function to figure out what the y value is, because I need to know where does y equal 5 live with this, right? If I plug 2 into it, it shouldn't matter. I plug it into x squared, I get 4. Square root of 16, I get 4. It shouldn't matter, you follow? Because we should get the same y value out from both. There it is. but I'm spinning it around the line y equals 5. You with me or not, folks? Okay. Now, once again, we're doing the disk method. That means we're going to be chopping up the axis of rotation. And when you chop up the horizontal line, y equals 5, you're really chopping up what values? You're really chopping up the x values again. You with me or not? Okay. Now, as always, you draw in the representative rectangle. Here it is. And you imagine spinning that rectangle around that axis, and if you imagine moving that around, there's going to be a gap. You follow? The representative rectangle doesn't reach the axis. So that means we got to think about the whole minus the whole. So the whole would be from x squared all the way up to 5. And then the whole would be from root 8x up to y equals 5. So once again, this is the whole, H-O-L-E, and the green here is the whole, W-H-O-L-E. So do we understand, are we good at spotting when you need to do the subtraction versus when you don't? Right? When you move your rectangle, if the bottom curve isn't flush against the axis of rotation, you're going to have to do this kind of thing. So here we go. Now we're going to figure out the volume here. And I think back, the volume of a disk is pi radius squared times thickness. I'm chopping up the x-axis from 0 to 2. So the thickness is going to be x. Let me keep it color-coded here. Keep it color-coded here. Put the big minus in there. So once again, we want the volume of the whole thing minus the volume of the whole. Okay. Now add red. Okay, so pi integral. I'm chopping the x-axis up from 0 to 2. My thickness then is going to be dx. I need the radius squared. Once again, the radius is the distance from the axis of rotation to the curve. All right? I'm chopping up the x-axis, so I can get the radius. Once again, the height of that rectangle, that's top minus bottom. Do you see how what we did yesterday is coming in here? Because that representative rectangle. What's the top here? That's y equals 5. Minus the bottom here, which is x squared squared. So let's take a minute, make sure we're all cool with what that integral is calculating. Pi radius squared thickness. Thickness dx. Radius is the distance from the axis of rotation to the curve. In this case, it's since we're chopping up the x's, we take the top minus the bottom. There it is. And then what would the next integral be? This would be pi integral 0 to 2. What's the radius here? What's the top? What's the bottom? The top of this rectangle is y equals 5. The bottom of this rectangle is, there it is. Make sense or not, folks? And the y-axis. All right, so same region. Now we're going to spin around the y-axis. Oops. Oh, not that. Okay. So now we're spinning around the y-axis. And since we're doing this method, if we're spinning it around the y-axis, that means we're chopping up what axis? The y-axis. So here we go. We're chopping it up this way now. You follow? And we know from our work before that the intersections on the y-axis are going to be 0 and 4. And what's the first thing we do? We draw in that representative rectangle. There it is. Now, does the bottom of that rectangle touch the axis of rotation? No. That means we're going to have to use the washer method. We're going to have to take the volume of the whole thing minus the volume of the hole. So we got to take the volume of the hole minus the volume of the hole. Because of that gap. So here we go. You got your pi. We're chopping up the y-axis now. We're chopping up the y-axis from 0 to 4. My thickness is going to be dy, but I got to figure out what that radius is. So as always, for the disk method, the radius is the distance from the curve to the axis of rotation. In this case, we take the right minus the left, but we have to have everything in terms of y's now. You follow? So I need a function of y. So I look here for this curve. I need to know what this is, x in terms of y. So this would x be, if y is x squared, then x would be what? Yeah, technically plus or minus y, but which y values are we looking at here? Which x values are we looking at here? Positives or negatives? Positives. And then we're going to the y equals 0, or the y-axis, aka x equals 0. So for this here, the right minus left would be the square root of y minus 0, which is just the square root of y. Is everybody cool with that? Minus pi integral 0 to 4. I need the radius squared dy. I'm chopping up the y-axis. I need to take the right minus the left. Here, for this rectangle, this is the right curve minus the left curve. So if y equals root 8x, what's x as a function of y? What would I have to do to get rid of the square root? Square it. What would I have to do to get rid of the times 8? Divide by 8. So right minus left would be a y squared over 8 minus 0. And so that would be my volume. Volume would be pi integral 0 to 4. And once again, don't be surprised. I think we do this on the handout too, just to get you used to it. Whoops. So this would be root y squared, which would just be y, dy, minus pi integral 0 to 4. What's y cubed squared? Or excuse me, what's y squared squared? This is y squared. Y to the 4th over 64 dy, and then whatever that works out to be. Okay? You see what's happening or not, folks? So, to review, area by slicing. You've got some kind of base, and you've got cross sections. with area A of t. Your volume is the integral from A to B, A of t dt. We're getting volume by taking area times thickness. Okay. If this is your base, you want to draw on your representative rectangle. Bless you. The thickness is either going to be the dx or dy, depending on what axis you're chopping up. A spatial case of this is when you have solids of revolution. Today we talked about the disk method. Right, tomorrow we'll talk about a different method. Today we talked about the disk method. The primary formula we're using here is pi times the radius squared times the thickness. The thickness, that's either your dx or your dy, whichever axis you're chopping up. The radius then is either going to be top minus bottom or right minus left. This is the distance to the axis of rotation from the curve. You're always going disk method, just like in the polar areas we talked about on Monday. Polar areas always go from the origin out to the curve. The radius for the disk method always goes from the axis of rotation out to the curve. Once again, washer method, how will you detect a washer method situation? If you have a gap. When you set everything up and draw it, you draw your rectangle there. If you find that you've got a gap between the curve and the axis of rotation, once again, I like to think of the washer method as being the whole minus the whole. I think it's the humidity. It gets humid and it acts up. So the washer is going to be the volume of the hole minus the volume of the hole. The volume of the hole is going to the outermost curve, and the volume of the hole is going from the rotation axis to the innermost curve. Okay? If you follow those principles, you'll be fine. If you try to memorize formulas for each and every case, you'll go crazy in this section. Okay, so just stick with the basics. Okay, that's it for 6.3.